Okay, thank you everyone for coming to my talk. Today I'm going to talk about the effects of wind on the shape of overturning overturning waves. And we're going to use the surf ranch as a laboratory. So first I want to thank and note that this work was funded by the Mark Wolfinger Surf Zone Processes Research Fund. And this is a collaboration between folks from Scripps Institution of Oceanography, the Army Corps of Engineers Field Research Facility, and the World Surf League's Wave Company, as listed above. And so just to set the stage, I'm going to show you a photograph here of a wave at the surf ranch with offshore wind, and then another wave here with onshore wind. And what you can see is that there's qualitative differences between how this wave is overturning. The overturn means how the lip of the wave that jets out in front of the wave. You can see here it's a fairly large overturn, and here it's a fairly small overturn. And we're going to be sort of quantifying these things and looking at the effect of the wind on it. Okay, so here are the same two photographs. So first I just want to talk about, so why is overturning wave shape important? Well, it affects how much turbulence and the intensity of turbulence generation, which picks up sediment, moves sediment around. So it affects sediment transport. And why would wind affect overturning wave shape? And this is something I can't answer immediately, but or quickly, but surfers have long understood that offshore wind leads to larger and more square, i.e. 1-to-1 aspect ratio overturn. So it's easier to fit inside this overturn if you're trying to get tubed as a surfer relative to this one. And there have been some previous studies on wind effects on wave shape, primarily laboratory studies here, Douglas and King and Baker, where they're looking how the wind affects the breakpoint location. Other studies on the shape of shoaling waves, and only with onshore wind. These were, some modeling studies and some theoretical studies in deep water and on flat bottoms, and then a combined wind and shoaling study, but basically prior to breaking. So it's sort of like, how is the shoaling process influenced by wind? And more importantly, to really understand the effect of wind, you need controlled observations, right? Because in real life, you have variable bathymetry, and you have variable wave fields and tides and stuff like that. And all these things also, of course, affect overturning wave shape. And so here we're able to do a study in essentially a laboratory study, but at field scale. And so the surf ranch, it's in Central California. This is an aerial photograph from the northern side to the southern side. It is approximately 600 meters long and 50 meters wide. And we had a MET station deployed. We had a drone to get movies. And we had a wave staff and a Velodyne LiDAR mounted on the rig. The rig is an aluminum tripod with a pole on it. And this is the LiDAR, and the LiDAR was then mounted like this, and this is a wave sort of like passing by. And waves are generated at the surf ranch by this thing here called the vehicle that gets pulled on some tracks up and down the tank, and it generates essentially a bow wave that propagates obliquely incident up a slope, and then it reaches a constant water depth bar where the waves break, and then a trough, and then there's another slope onto a beach. We also define a surf ranch coordinate system where X is the cross basin direction, and Y is the along basin direction. And it's defined such that 0, 0 is the location of the rig here, and schematically it's located at that location. Okay, so here are, just to provide a little bit more context, here are two movies of two waves, one with offshore wind. We call this a right wave because the surfer surfing on this would be traveling to his or her right. And then down here we have a left wave where a surfer would be traveling towards the left. And you can see with the onshore wind, there's again a qualitative difference in the size of the overturn. It'd be hard for a surfer to fit into this barrel, much easier to fit into that overturn. Okay. So now getting a little bit more quantitative, we have two examples of two different waves, a left wave on the left and a right wave on the right. And the first things are just some photographs from the end of the basin And one of the things that we're highlighting here with the magenta diamond is the location where the free-falling lip of the wave or jet of the wave impacts the surface and where the splash up occurs. And we're going to call this the breakpoint, define this as the breakpoint location. And then at the wave staff, as the wave passes by the wave staff, we can measure from the maximum to the wave staff, the location before the wave. We can measure for each individual wave, the wave height. Okay? And then from drone images and the LiDAR, we can sort of like overlay the LiDAR observations from the drone images. And so the LiDAR is such that blue colors are lower elevations and yellow gold colors are higher elevations. So you can see there's a nice match between what you see visually from the drone in, again, surf range coordinate systems relative to what the LiDAR measures. Okay, now one key thing here is that the bathymetry is fixed. So we're controlling that. There's very slight water level variations from day to day, but the bathymetry is fixed. And in total, we have 22 really similar waves, and but with a whole bunch of different variation of wind. And there are 11 left waves and 11 right waves. Okay, so the first thing we want to do is get a quantitative value for the breakpoint location. And so we take the drone images and we identify the location where the lip overturns and the splash up begins. And those are the red dots shown here for a left wave and the red dots shown here for a right wave. And then what we do is we average this for 20 meters prior to the wave coming to hit the rig to develop a breakpoint location. In addition, we also define, it's going to be natural to do this, to find a wave coordinate system where x tilde propagates in the direction of wave propagation. So it's this way for a right wave, this way for a left wave, and then y tilde is always in the offshore direction. So that means that in this case, you have for the left waves, you have a right-handed coordinate system. For the left wave, you have a left-handed coordinate system. Okay. In this coordinate system, in this x tilde, the wave speed is almost 7 meters per second. And what we do then is we rotate the wind into this coordinate system. So we take the dot product of the wind with a direction of x tilde to get UW, divide that by C. This is a non-dimensional parameter on the wind speed. It's a wind speed to the phase speed of the waves. And if it's greater than 0, it's onshore. If it's less than 0, it's offshore. Okay, so now let's take a look at some LiDAR observations of wave overturning. And again, what we're going to do is, because this is the y tilde direction, we're going to look at the LiDAR observations as a function of x tilde, and we're going to have the view looking into the overturn, as that white arrow suggests. Okay, and this is going to be analogous to a view looking into the overturn like this. And so there's two waves, and there's two waves here, and we're showing a left wave to the left on the left column, a right wave on the right column. And these are a function of x tilde, so this is the direction of wave propagation in Z. And what we're doing in the top row, middle row, and bottom row is we're showing consecutive times. So these are separated by 0.3, each one of these is separated by 0.3 seconds. Okay, and we're showing all y tilde, so all directions along in here. So perhaps it's easiest to just see on the right wave first. What's colored is the y tilde. So when the colors are darker, you're more you're further offshore, and when the colors are lighter, you're further inside, further onshore where the wave is completely overturned. And so the dark colors, you can see the face of the wave here, and then as you go further in y tilde, you see the colors get lighter as the wave is overturning and falling down. And then if you look from frame to frame, you can see that there's really not that much variation, clear variation in the overturn. And similarly, on the left wave, well, further offshore, we didn't visualize this overturn completely here. But as you go further, the overturn further onshore or further in time, you see the overturn becomes more and more clear. And there's some similarity. This is also pretty uniform in this direction. Okay, so now what we're going to do is we're going to look at a single wave at a single time. And again, we're going to look into this barrel direction here. And what we're going to do is we're going to take slices in the y tilde direction. So in panel A, what we're doing is we're taking data from just this region here, a 2 meter wide region here, and plotting all those data points. And what you can see is the face of the wave, and you can see the overturn starting. All right. And then as you march further in this direction, and each one of these is marching 60 centimeters further over, is you can see now more of the overturn, but less of the phase. Here you're really starting to clearly see the overturn. Here the overturn is closed and has closed. And now here it's further closed, but you don't really see inside the overturn anymore. And at this point, you're seeing splash up and some of the overturn and a little bit of the wave in front. And so you can use this looking in this direction as also as a proxy for time. Oh, yes, and then the cyan color represents what's happening further. And so to quantify these observations, the wave overturn, we're going to use a functional form from Long and Higgins. This has been used in previous overturning studies by Blenkinsop and Chaplin and O'Day et al. And the functional form looks like this. And this functional form has two key parameters in the width of it and the length of it. And this results in an area that scales with L times W and an aspect ratio that's W times L. And basically this functional form then is fit to 2 meters of a long crest data that contains the overturn. And what does that look like? Well, it looks something like this. So here is a 2 meter swath of 2 meter alongshore swath of LiDAR data. And the black dots are the points that were included in the fit. And then what you can see is the W parameter and the L parameter associated with that fit. And again, this is sort of like looking like what you're looking like when you're looking into the overturn. And then here are just some example of overturn fits. And so what I'm showing here in the blue colors is showing all the delta Ys. The 2 meter swath that is actually included in the fit is sort of like the green colors and the gold colors, and the points that were chosen in the fit are the gold colors. And so the thing to note here is that you can see clearly that there's that these two overturns have different shapes and different aspect ratios. Okay, so now to examine the wind effects on wave shape, and again, here's the sample onshore wind and offshore wind. We have 3 wave parameters: the non-dimensional breakpoint location, so this is the change in the breakpoint divided by the surf zone width, which is about 20 meters surf range. The non-dimensional area, which is the area divided by the wave height squared, and the aspect ratio, W on L. And we've got a non-dimensional parameter for the wind speed, this UW on C. And the hypotheses we're going to test are essentially similar for all of them. The offshore wind leads to breaking closer to shore. Onshore wind does the opposite. Offshore wind leads to larger overturn area, and offshore wind leads to more square overturns, i.e. larger W on L. And onshore winds do the opposite. So let's first take a look at the breakpoint non-dimensional breakpoint location. And just for reference, again, the breakpoint location would be here and here in these 2 photographs. So when we plot delta X BP divided by LSC against the non-dimensional wind speed, we see that there's a very nice, clear relationship between the 2. For offshore winds, it's the breaking is closer to shore. For onshore winds, it's the breaking is farther from shore. And there's a consistent relationship between the lefts and the rights. If we look now at the non-dimensional overturn area and the aspect ratio, we also see a nice clear relationship. So for strong onshore winds, the non-dimensional overturn is relatively small, and as the wind gets more and more offshore, it increases until it essentially saturates. And this is likely because the area can't just continue increasing because it literally is not a square, right? The breaking wave overturn. And similarly, the aspect ratio also has a nice clear relationship amongst the lefts and the rights. And the aspect ratio is smaller, so narrower barrels for narrower overturns for onshore wind, and larger aspect ratios for offshore wind. So consistent with our hypothesis. And so the conclusion here is that once you've isolated the effects of bathymetric variations, tidal variations, and such, the wind has a strong effect on overturning wave shape. And I'd just like to conclude by saying this work is in prep for Journal of Fluid Mechanics. There's many, many more details. This is relatively fast and stuff, things to discuss. So join me at the session. And I want to thank you again to the Mark Wolfinger Surf Zone Processes Research Fund and everyone that enabled this work. Thank you.